So now, whoops, come back on here. So the next part that we're going to look at is where our electrons exist. So now we've got kind of those old theories down for Lewis and Vesper and all that, but now we got to actually look at the exact orbitals on where those electrons are located, or at least a comparison. So atomic theory said we had s and p orbitals, which is all fine and dandy, but then as soon as we move into molecules, things start to break apart. And why do they break apart? Well, let's look at probably the easiest example of that would be something like methane. And if we look at methane, all of those bonds or orbitals, because that's where the electrons have to exist, need to be identical. Okay? And they need to be identically spaced to that 109.5 to match our Vesper system. And if we looked at the atomic orbitals for carbon, what we would see 1s2, 2s2, 2p2, we might make the first approximation that our second energy level is going to be the one that's going to be involved in those bonds. So we might look at our 2s2 and 2p2. And in that, we could go, well, there's 1, 2, 3, 4. That could explain the 4 different bonds, so 4 different electrons. That makes sense. But now how do we explain the bond angles being 109.5? If we look at the individual orbitals, and we say take the 2s, which we'll go ahead and call green here, is just a sphere, right? That's our 2s orbitals. And we look at our p orbitals that overlay over the top. Well, what's the bond angle between that s and p orbital? What do you mean angle? They're overlapping. How there's not an angle there. If we complicate things further by noting the other p orbitals, we would see that we're looking at a 90-degree at best case. With the overlap with the s, we have no clue what's going on. The p orbitals overlapping with each other are 90 degrees. Those aren't 109.5. So something is wrong here, or something has to change. And it does make sense that when we move from the atomic world to the molecular world, that we should see a change in bonding patterns because you have a different nucleus affecting where those electrons are. So we would expect some kind of modification of our orbitals. The question is how, and how do we represent that? Well, there's a couple different theories that come out of this. The kind of easiest one for us to manipulate and understand that does a pretty good job of explaining things is our hybridization theory. And that's the one that you already watched a video on, and we'll look at again here in just a little bit. And then we've got linear combination of atomic orbitals, or Lakow-Mott molecular orbital theory, sometimes referred to as frontier orbital theory. And those systems usually require a lot more in-depth kind of analysis that are really outside the scope of this class. So first we'll look at our hybridization. What we're acknowledging within the hybridization theory is that we're trying to get to a system with 4 identical orbitals. And how do we explain those 4 identical systems? Well, what we can notice is that what we're starting with is 4 atomic orbitals. And if we treat orbitals as something like matter, okay, we can't create or destroy it, but we can kind of mutate it and adjust it. If I need 4 molecular orbitals that are all identical, but I don't have 4 identical orbitals, atomic orbitals, what I can do is take all of these and mash them together like Play-Doh. Okay? Make them one big giant pile, average them all together, and now pull out of it 4 new orbitals. Okay? And that's effectively what hybridization theory is doing. So when we say don't use magic, it's kind of magic. Okay? We're saying that we have 4 orbitals necessary in our hybrid. That means we need to use all 4 of our atomic orbitals, 1s and 3p, and we would generate these new orbitals. The part that sometimes is confusing behind this is, what do we call these new orbitals? As we said before, we call them whatever we want. What we decided as a group of scientists was that sp3 makes the most sense because it represents what orbitals were used to make these new orbitals, okay, what atomic orbitals. Each of those orbitals is an sp3 orbital, okay, each one, not one is one and one is another. They're all individually sp3 orbitals. We're just using that name to kind of represent them because that way it explains where they're coming from. Why is that important? Well, if I encounter a different system, say like the methyl cation that had only 3 groups of electrons, well, now I would take the 1s and 2p's. Okay, so if we remember that methyl cation, people often complain that I don't reference backwards and then show things, so let's show it. There's our methyl cation. There's 3 groups of electrons. So we need 3 identical molecular orbitals. I'm going to take 3 atomic orbitals and put them together. For those of you saying, why don't I use just all 3 p orbitals? Bond angles, the p orbitals aren't 120 degrees away from each other. So that's one explanation. The other explanation is that if we're going to combine things to make orbitals, we want to use the lowest energy orbitals possible. That's why we bring in the s. Okay? And as we bring in the s, that means we're using 1s and just 2 of the p orbitals. We mash those together to create these new orbitals. These new orbitals we'll call sp2. I would now have 3 sp2 orbitals. Okay? Within that, I can't create or destroy, and the destroy becomes the new part. I have a leftover p orbital. That leftover p orbital is what explains the cation. That positive charge means there's another place that we can put electrons. Well, an empty p orbital, unhybridized, is a perfect place that we could place electrons. So that cation is represented by the empty p orbital, or the unhybridized p orbital. And that's fantastic. Our theory helps to explain how that comes about. Okay? As we continue to go through, we can come up with other hybridization schemes where we end up with 2 SPs and 2 leftover unhybridized p orbitals. And so really what we're trying to go through and do is just create a system that allows us to explain this. You'll note that there are some shading and unshadings behind those orbitals. We'll look at that when we look at molecular orbital theory, because that's when we start to see how these things overlap. At this point, we really just want to understand what must those atoms approximately do to achieve the bonding patterns that we're used to seeing. Okay? So within the video that you already watched, we looked at the hybridization for boron in BH3 and carbon in CO2. Well, now what we're going to do is tweak it a little bit, and I want to know the hybridization for the bonds. Well, that's interesting. In the video, we looked at the hybridization for the atom, in fact, the center atom, boron and carbon. Now I want to know what the hybridization is for the bond. So let's stick with BH3. Right? BH3, we're going to simplify and just look at B and H. Okay? So 1B, 1H. So here's our boron, and here's our hydrogen. And if we were to go through and evaluate the hybridization of our boron and our hydrogen, well, so what we should do is think to our Lewis structure. There's our BH3. We know there's no lone pair because boron only comes in with 3 valence electrons. Each hydrogen comes in with 1, so we have an empty slot, okay? Only 6 electrons around it. That means our boron comes in as sp2 hybridized. If we were to go through and look at that, that would mean we would have 1, 2, 3 sp2 hybrid orbitals for the boron. We would also have left over 1 p orbital. If we went through and look at the hydrogen, it only has 1 electron in the 1s orbital. There's no p orbitals to evaluate. It's only an s orbital. So what we're looking at interacting to make the bond between the boron and the hydrogen is interacting in sp2 and that 1s orbital. Note we aren't going to interact that unhybridized p orbital because that p orbital is higher in energy. So we don't evaluate that. So if I'm going to look at the connection between these, the bond that makes these up, I'm taking a 1s orbital from the hydrogen, and I'm taking an sp2 hybrid orbital from the boron. So if I want to explain the hybridization of that bond, it's a boron sp2 with a hydrogen 1s. That's it. That's all I'm asking for. Okay? What happens if we move to CO2? CO2 we're going to make a little bit more complicated. And the reason CO2 is going to become a little bit more complicated, because if we look at its Lewis structure, we might have that one and say, well, it's the same on both sides. But remember that resonance structure, where we could have shown something along those lines? That's going to make things a little bit trickier, and we're going to have to be a little bit more careful with how we approach and balancing this one out. Okay, so if we go ahead and start with the carbon, and this is an extra long line because I'm going to do it both directions. The carbon, either way we look at it, is sp hybridized. So we'll have our, whoops, I don't need to show the orbitals. We'll have our sp hybrid orbitals, and we'll also have a p orbital left over. Whoops. Yeah, 2 p orbitals left over. Okay, so total for our carbon, we started with 4 atomic orbitals, and we end up with 4 potential molecular orbitals. Okay, it's a little bit weird to say that because these are still technically atomic orbitals because we're looking at the hybrids. If we now draw on our oxygen, well, in the red structure, our oxygen starts, you might say, well, it only has one group of electrons, it's not hybridized. But remember, lone pair electrons that I said I was always going to include, and I forgot, I apologize. But there are lone pair electrons around those. So if we're looking at our red structure, that red structure is oxygen is sp2 hybridized. And so if we were to go through and do that, we need 3 groups of electrons for our oxygen. 1, 2, 3. And these would be our sp2, and we would have a p orbital left over. And if we looked at the other oxygen out the other side, we'd have the same system. 1, 2, 3 with our sp2 and a p orbital left over. If we're going to go through to count this out, we've got our non-bonding pairs of electrons out in those systems on our oxygens. How do we then create our bonds? Well, we're going to take 1 sp from our carbon and 1 sp2 from our oxygen. We'll also take 1 sp from our carbon and 1 sp2 from the other oxygen. That would explain a single bond in both cases. Okay? How do we explain the presence of the double bond? Well, the presence of the double bond is now the overlap of the p orbitals. Okay? And that's where those orbitals are coming from. That's how we explain this patterning. Okay? So in this case, we end up now with 2 different types of bonds. We've got the type of bond that is connecting, whoops, let's color that out right, sp2 from our oxygen with an sp from our carbon. Note the important part here is S and S, and then at the same time we have an oxygen P and a carbon P. Okay, note P's now. So when we're talking about our bonding, we're now seeing the existence of a second type of bond. We're getting the direct overlap of the S-type orbitals, okay? And we'll look at the direct and indirect later. And we're getting this kind of secondary overlap of orbitals being our p orbitals, okay? Which I would call indirect. Okay, and I'll draw that out in a second so we can see what I'm referencing by direct and indirect. These 2 different types really tie back to the orbital types being used. The indirect used p orbitals and the direct used s-type orbitals. Note I'm saying s-type because it's sp versus sp2. So as long as I have an s-type orbital involved, I'm looking at this direct overlap. We now have the existence of 2 different orbitals or types of orbitals to explain the bonding pattern and why I can get more than 2 electrons in that relative space, because the electrons aren't occupying the same space. They're occupying slightly different spaces. How do we see that? Well, it's going to become a little bit more apparent if we show the orbitals kind of in a cartoon fashion. For that oxygen, we had sp. For the carbon, we also had an sp. Okay? Here, those orbitals are directly overlapping. For that also oxygen, we had a p orbital. And for the carbon, we had another p orbital. Note that they aren't getting close enough to actually overlap. But as long as those orbitals are in the same plane, the electron can tunnel through space. Okay? And that's causing that indirect overlap. The p orbitals aligning in the same plane are what allow for the overlap. Right? And that's what's happening there. That's why we're getting that. Here's an interesting question that pops out though. If that orbital, that red one, is being used to make the direct overlap there, how do I create another double bond out the other direction? Right? Because that orbital is already used, I can't use it again. So what has to happen is that I have to use a different p orbital. Right? And when we're talking about these orbitals, we can call this x or y and z. And we're looking at the p orbitals overlapping on the y-axis or overlapping on the z-axis. The x-axis in this case is the one where our bond is forming. Okay? And so it is that p orbital now coming in and out of the plane of the paper that is overlapping with the other oxygen to create the other pi system. This becomes important as well because now these electrons cannot jump over there. Okay? And therein lies an interesting dilemma. If we think about how we moved from our double bond structure to the triple bond structure, did these electrons jump over there? Okay? They physically can't. According to this model, they can't do it because those orbitals aren't in the same plane. Okay? And as soon as I can use pens, I will use pens, but the problem is I don't want to get rid of my drawings. So let's go back and think about how we got the triple bond. What happened? The electrons from our oxygen come in, forcing those electrons out. Okay? That's how the triple bond formed. So what had to happen was the electrons in an sp, kind of off axis, rotated up to be in the plane of the p orbital. Those shuttled in so that they would overlap with that pi system. Well, if as soon as it overlaps with the red one, God, that looks awful. The electrons that are being shared from the other oxygen must kick outwards. And that's what's causing that shift in the electrons. The arrows that we're using literally mimic how the molecular orbitals change to explain the different bonding patterns. Right? And to get to that triple bond, our one oxygen out the other side is no longer sp2, it has to become sp. And it has now two p orbitals that are left open. One might be that pz, great, it overlaps. We had that before. That remaining one is the y. Those or that orbital can overlap with the other one, but it can't overlap simultaneously, which means when it overlaps, it breaks the connection to our other oxygen and we lose the double bond out the other end. Okay? And as I say something about pens, I realize I don't have two pens handy, but I do have some pencils. So we're going to delete everything here. So if you wanted to continue to look at this, have mercy on your soul. Let's go ahead, come on now, work with me, and take a real quick look at what we're talking about when I'm talking about these p orbitals. So when we're mentioning the p orbitals, they're effectively kind of on the plane. So if we look at just atomic theory, we got to go that way. My hand's kind of in the way. We get the axes, the XYZ axes. Okay, so now let's just, because we said on this axis, that x-axis is where we're forming a bond. We don't have any p orbitals. That's hybrid. So we're looking at just these two systems. Okay, if I want that carbon to form a secondary bond with my other hand over here, okay, a pi bond using those p orbitals, that hand has to have a parallel p orbital so that the electrons can tunnel. Okay, that's really hard to see right on that axis. So maybe let's say instead of it forming on that z-axis that's coming in and out of the plane, we form it on the y. Now you see that those are both aligned. And really the important part here is not so much saying, oh, well, they look aligned. It's here. Now our electrons can jump back and forth. But what happens if I do this? Is there a significant overlap of those orbitals? No. Now I've lost it, so now the electrons can't jump. Only when the electrons are in a perfect alignment do you get the electrons being able to tunnel that large empty white space. Okay? Because remember, here's your direct overlap. They can tunnel through that. When they don't directly overlap, okay, they have to align in the same space so that your electrons can jump. As soon as we turn, there's now too large of a distance for them to tunnel, and we don't see that bond forming, or we don't see the electrons being shared between the atoms. It's all about that proper orbital alignment. Okay? XYZ labeling ultimately doesn't matter, because once you've nailed down, said this is X, well, then you can nail down the other ones and decide which one they want to be. So that's not a big deal. Don't get bogged down in the XYZ. Get bogged down in the fact that we're looking for orbitals overlapping. And that becomes the big crux of what you're trying to get to. Right? Thought I was going to draw something else, but I just completely blanked on it. I think I've covered what I wanted for those. So what we're looking at is how those orbitals overlap. What you're doing is identifying the hybridization for each atom, and then looking at what orbitals are going to connect to make that bond. Okay, which does remind me of what I did kind of want to talk about, and I was gesturing with the pens. If we run into the system where we have hybrid orbitals overlapping, note that we get that direct overlap. That direct overlap only comes about if you're using s-type orbitals. If we look at our p orbitals, the p orbitals are perpendicular to that axis, and because of size and directionality, as soon as the s-type overlap, the p can't get closer, so they never actually directly encounter each other, and this is where we're getting the indirect overlap. Okay? And this is what I might call p-type, because you're using p-type orbitals. Okay? This is where, if you think back a couple videos, we talked about s and p electrons being able to move. The s electrons we couldn't move, the s bonding, because if we move them, we're breaking that connection between those atoms. The p-type, however, we were allowed to shuttle around because we could have different orbitals open up at different locations, allowing that connectivity. So we could reference them as p-type and s-type, but really what they get labeled as is their Greek, sigma and pi. And so when we look at the bonding patterns in, say, CO2, what you might have heard back in Gen Chem is that we have two double bonds. And really, that's a load of crap. It's not two double bonds. It's two sigma bonds. Well, aren't sigma bonds only single bonds? No. Single bonds are just the first connection between those. To get to a double bond, I need another bond type. That other bond type is a pi bond. So when I look at the bonding patterns in CO2, and we're just going to simplify it and just look at half of that molecule, what I need to acknowledge is that there is a sigma bond between the carbon and the oxygen, and there is a pi bond between the carbon and the oxygen. Referencing bonds as sigma double or triple for pretty much the rest of OChem is a bad idea, because bonds don't react as single, double, or triple. They react as pi bonds or as sigma bonds. And the sooner you can shift your focus to what are the orbitals that are holding those electrons, instead of saying what are the bond types that was a fictional description anyway, the better you can get towards predicting chemical reactivity and where those chemical reactions occur, right? And that's pretty cool, okay? So some things to remember: the number of orbitals in your hybrid equals the number of electron groups, okay? So if I have 3 electron groups, I need 3 atomic orbitals. Start with S, that's 1, sp2. If I need 4 atomic or 4 molecular orbitals, I need to start with the S and 3 molecular orbitals. What if I have 5 molecular orbitals? Well, I start with the S and 3p, and I come up short. Thankfully, it's OChem. We don't really care, but think back to Gen Chem. What happens? The 5th comes from a d orbital. The d orbitals are allowed to contribute, but this is OChem, and we don't deal with the d orbitals because that's just confusing. So what does this mean for us? Okay, so there are some effects that come out of this that turn into some pretty drastic results. So I asked you to draw out the Lewis structures and provide the S character for the carbons in each of these drawings. Okay, so if I was to attempt to draw these really quickly, we've got our carbons and our hydrogens all the way around. And if we were to look at the S character, well, this is an sp3 carbon. One of those orbitals, or one s orbital, went into this out of a possible 4. This is 25% s. If we go through and look at C2H4, we'll notice that we had 1 s orbital come out of 3 possible. This is 33%. And if we move to the last one, C2H2, we have sp hybridized, which is 1 out of a possible 2, 50% s character. So that's what we're being asked for within that, okay? Why do I care? Okay, well, if it's more s character, what does that mean for the structure? So think back to the drawings that I had set up. If we look at our s orbital and our p orbital, the hybrids are somewhere blended in between. If we're an sp3, we are less s character, so we'd be up here. There's our sp3. Let's color code it because we can. There's our sp3. Our sp2 is a little bit closer to the s, and our sp is kind of halfway in between. Okay, what does that mean for us? Well, the p orbital is itself larger than the s. Not by a lot, but it is larger. The s orbital is more compact, which means the more s character we get, the smaller we get. You say, well, why do I care? Well, the smaller that gets, the smaller the bond gets. Okay, or the electrons, the electrons in that bond get sucked closer towards the carbon. Is there something that describes the ability for one atom to attract bonding electrons closer? Electronegativity. That means the sp atom is more electronegative than the sp3. Right? Okay. Again, you might be saying, and why do we care? Okay, well, let's try something else. Let's pull at some Gen Chem knowledge, and it might even be 152. I know I address it in 152 when I taught 152. Let's look at HF versus H. 2 isn't super important. O. Which one of those is a stronger acid, HF or H2O? I'm really hoping you say HF, because that's the answer. Why is HF a stronger acid than H2O? Well, fluorine is more electronegative than oxygen. So you mean changing electronegativity takes a compound from a relatively neutral don't kill me to a death? Yes. Take a look back at our hybridization effects. An sp hybridized carbon atom is more electronegative than an sp3 hybridized carbon atom, which means the sp hydrogen is also more acidic. understanding hybridization can help to explain the difference in acidity for our carbon-hydrogen structures. That's wicked. Okay? And it becomes a really important pattern that we need to know. And when we talk about reactivity, which we will, it's going to come back then, and you're going to have to kind of remember it. So the sp atom, more s character, holding the electrons tighter, more electronegative. The more electronegative the element, the more acidic a hydrogen would be that was connected to it. That's kind of cool. So they all kind of stack in with each other. For those of you saying that is mind-boggling and there's no way I would ever remember that, there's a cheat. You memorize that if you have that sp carbon, that hydrogen is acidic. Okay? So you don't have to know the why in a lot of these cases. You can get away with just blatant memorization. This goes back to where are you going to define that line? Do you understand more or do you want to memorize more? If you got a great memory, you will test the crap out of it in OChem. If you want to understand what's happening, that's when you need to be thinking about all of these pieces and how they stack and interact with each other. Okay? So atomic orbitals, overlaps in C2H4. So if we could draw out a Lewis structure, electron groups, the hybridization, all of that, okay, what we should end up with is something goofy looking like this. Okay? And this, you might also say, meh, it's a pretty picture. Okay? Thank you to our textbook for making it. Nice, pretty pictures. And you might say, well, why do I care? Okay? Well, the why I care, again, is going to come from how we look at this. And so a lot of OChem is changing your viewpoint on the molecule and deciding how does that change my interpretation. Okay? So in this case, we're looking at it kind of from the side. So if we looked at it, I think I can pull this off. Let's see if this works. So we're looking at it kind of from the side. Okay, that's the point here. Okay, so we've got the model built out for us. For the record, not my favorite model, but it works. Okay, and I don't know where my favorite model kit is. Okay, so that's our system. And if we changed our viewpoint and looked at it from the side, we still might not really care and be like, again, why does that matter? Okay, well, it matters when we go back and look at the molecular orbitals. Okay, look at that orbital diagram, and if we're turning it on that side, we're now putting, come on, pen, a carbon in front, we got a carbon in back, and what I'm concerned about, okay, believe it or not, is the p orbitals. So all I'm doing is taking that model and I'm grabbing the leftmost carbon and I'm pulling it out of the plane towards you. And that leftmost carbon, whoops, is going to be that guy, and the rightmost carbon will be that one. And the really important part is looking at the p orbitals. Okay, so if I do that, the p orbitals are vertical in the plane of the paper now. And if I take it and turn it, they're still going to be vertical because I'm not rotating it. I'm just pulling it out, which means there's one and there's the other. Okay, in the back, showing really big. Why is that important? Okay, well, the model kit intuitively gives it to you. Okay, the molecular orbitals don't intuitively give it to you. Remember, we said the electrons had to be aligned in the same plane to be able to jump. Frickin' pens, pencils, whatever they are. Okay, right? P orbitals. And we grab them in the middle to make it a little more representative. There we go, p orbitals. And we turn it. There they go, they're aligned. And you're like, again, why do I care? Okay, well, let's switch it up. Let's say we didn't have p orbitals. SP. Turn again. Okay, not a big deal. Okay, what happens if I spin this pen? What happens to that overlap? You're like, it's kind of dumb, dude. It just stays the same. Good conclusion. I like that. That was awesome. So let's try it back to the p orbitals. What happens if I spin? Does the overlap stay? No. Now the orbital is not overlapped. What happens to the ability for the electrons to jump? They can't. Electrons can jump. Electrons can't jump. Well, what do the electrons want? Well, what do you want? Do you want to be in a big lecture hall, or do you want to be confined in a 5x5 box giving a lecture, not to give anything away? Right? It's a lot more interesting to have that more space where you can roam and breathe and exist. Okay? Being confined is not a happy space. Electrons can jump means they can move more places. Electrons stuck, they can't move. What does that mean? When we look at a pi bond, it prevents rotation because electrons don't do it. Don't. Right there. Leave it right there. Let me jump. And as soon as you try and rotate, that now goes high in energy because the electrons start freaking out. That means pi bonds don't rotate. Sigma bonds do, because that overlap never changes through that rotation. If we look at our model actually does it perfectly for us. Because if I look at the sigma bond, I can freely rotate that atom. I know it's super obvious that you can see that white ball spinning like crazy there. Okay, but trust me, it is. I'm not just pretending with my hand. Okay? The pi bond between the carbons doesn't rotate. It doesn't allow for that. I can't just spin it. That's because the model kit is designed to represent the molecular orbital system that we're looking at and that hybridization. Okay, so changing our view on that molecule allows us to see a little bit more information, and that's really neat. Okay, that's one of the reasons why hybridization theory is so important, is because it allows us to draw some of these conclusions without having to pull out a supercomputer that we might need for other methods. Okay, what this then introduces is this other concept of pi bonds and cis versus trans. So if we take a look at our top cases here, we've got a system where these R groups are on the same side of that pi bond versus on opposite sides of the pi bond. Right? And if we were to look at model kits, those R groups, those red balls, are on opposite sides of the pi bond, and because I can't rotate, there's no, I was going to overlay it on the freaking computer screen, okay? There's no way I can get that to look like the one on the left where they're on the same side, okay? Because I can't rotate that. So we could pull out another model and we could align them and we can see that that's what's happening. That's what we're trying to visualize. Because I can't interconvert between these, I need to be able to name them in such a way or describe their shape in a way that allows me to interpret and differentiate them without having to draw out the structures. This is where we encounter the terms cis and trans. Okay, cis means on the same side. Okay, so these are on the same side of that double bond. Okay, so we're drawing the double bond in between. That's kind of our line. They're on the same side, or they're on opposite sides, and that's trans. So what we need to be able to do is to look at a molecule and decide, is this cis-trans thing going to be an issue? Okay? So we've got 4 examples shown below. Okay? You should be able to go through and identify the molecules that allow for cis and trans. Okay? So when we're saying, do they have cis-trans isomerism, if you rotated the double bond, would you be able to tell a difference between your pre-rotation and your post-rotation? With that, we'll go ahead and look at a couple of them. Okay. Think back to the pattern that we have up above. Okay, we need 2 kind of distinct groups to be on opposite sides of each other. Okay? And note, when we're doing this, we are not showing it with the R groups like this. Because if I did a rotation here, would I be able to tell where the R groups were? Okay, I'd still have an H up, R, and R. So what we're talking about in cis and trans is if you rotated the double bond, could you see a difference? If you can, you have cis-trans isomerism. So let's take a look at the last one. Extra tricky because what we did was imply hydrogens. So we could go through and show those implied hydrogens. If I did a rotation about that bond, what would happen? Okay, well, if I rotated that, that hydrogen would be aimed up. This group would be aimed down. Well, up, down, clearly I can tell a difference, so it must have cis-trans isomerism. Look to the other side. Well, I can't tell a difference there. Well, does that matter? Okay, does that mean it does or does not? I can tell because the black part is aimed down. Okay, so the answer that I would typically give to that in class is a bit snarky, but it works, and we'll see if we can pull it off here. Buttons. Ta-da! What's my name? That's when you say Mike, and you should shout it. You know, let everybody know that you're got some stupid person teaching you. Okay? If I do, and now I ask again, what's my name? That's when you say Mike again. Say Mike. Okay. What's my name? Yeah, I think I heard you say it then. So, but did I look the same? No, right? Is the side of my, the back of my head? Those looked different, but I was still Mike. When we think back to that molecule, did the molecule actually change its identity, or did you just turn it? You just picked it up and flipped the molecule. Not a rotation of the bond, you flipped the molecule. That's where this becomes tricky. An apparent attempt to rotate the bond really was just a flip of the molecule, which means those were identical. You can't tell a difference between them, not cis-trans. Okay? We'll throw in one more tricky one before we end this video. Let's take a look at this last one over here. Okay, we could again throw in our hydrogens. Okay, and let's say we were to rotate that double bond. Okay, so if we rotate it, I'm going to rotate the bottom part, H, bing, bing, right? H. And you know, then I just continue out the ring, right? Okay. Would I be able to tell cis-trans isomerism here? Okay, this one becomes a little bit trickier. 1, 2, 3, 4, fifth carbon. Okay, and for those of you being like, dang, that looks really weird, you're onto something. Does this molecule show cis-trans isomerism? Would that structure be trans? Yes. Does this structure show cis-trans isomerism? No. Dang. This is going to be a good question to throw up in our discussion board, so I'm going to leave you to kind of explain why this is not a cis-trans isomer, and you should go through and take a look at those middle two and make sure you understand which one's cis-trans, if there is cis-trans for either of those. And with that, we are done with an extra long 43-minute video. I apologize for that.